Good morning, gang. Sorry I'm running a few minutes behind there. I was looking for a new pen in all of this moving chaos. I lost a bunch of pens. In any case, the surviving pens here, my black one that I've been using for the last couple of days has died. So I'm going to be working in a light orange color today. It comes through on the camera pretty well. But if you have trouble seeing it, let me know and I can switch to pencil. But yeah, that's it. So today we are going to pick up where we left off. You may recall last time we were talking about power functions. We introduced the arrow notation for end behavior. We solved a handful of problems relating to proportionality, and we should be feeling pretty comfortable, at least with power functions whose power is positive. So today I'm going to introduce power functions with negative powers, and then we'll see some of the similar problems in that setting. As I'm getting started here, if there are any particular problems from the homework that you guys would like to see, feel free to type those into the chat. I won't be able to do all of them, probably, but if there are some that are especially desired, I would be happy to take a look at those. I'm going to get the two homeworks for this week pulled up, launch the dot cam, and get moving. We should also be able to keep the copy open here. Okay. Let's see. Yeah. Oh, maybe not. All right, that's all right. We'll just do one at a time then. Okay. So negative powers introduce some algebra challenges that aren't present when dealing with positive powers. And I want to make sure that we're all really comfortable with the algebra before we get to the actual problem solving. So here we go. Like I said, if you have any problems reading the writing here today, just stop me and let me know. Oh shit, why is that? No, my orange pen is leaking now. All right, we're going to do our best. What's the 17th, the 18th? The 18th, right? Yeah. So this is homework 11. And I want to do also just a little review of exponent rules. Okay. So the rules for exponents are pretty important. Like if you take two numbers, A and B, they could be variables, could be numbers, could be whatever, and you raise them to a power. As long as these two numbers are being multiplied, right, as long as the operation that's going on in here is multiplication, then you can give that power to each one of them on their own. It doesn't work for addition or subtraction, but it works good for multiplication. And and division. All right, so powers do distribute nicely, like exponents do distribute nicely over multiplication and division. And then you have a kind of pair of rules talking about how to multiply like bases with different powers. So I have like a to the n times a to the m, that's a to the n plus m. And similarly, if I want to divide like bases with different exponents, I can do that like this. So here's like 1, 2. Another rule that we're going to use a lot is that if you take a couple of powers like a to the b, and you raise that whole thing to some other power, this is the same as a to the n times b. All right. And then there's some rules having to do with roots. The nth root of some number, that's the same as the 1 over nth power. So all of these are rules to deal with positive exponents, really. But then negative exponents come in like this. So if you have a raised to the negative n power, right? You have some number being raised to a negative power. This is the same as 1 over that same thing being raised to the positive nth power. And it's this particular thing that we'll be using quite a bit today. It's important for understanding how power functions of positive powers work. With negative powers work. Okay. So we've defined what power functions are before. We've done that a couple times. I don't want to like grind back through the definition. So let's just start looking at some power functions where the powers are negative. Are there any questions on these rules? Is anybody seeing this stuff for the first time? So I think I saw this stuff for the first time in college algebra because I dropped out of high school. If you are, it's all right, don't stress. If you're not, that's cool too. This rule will be very useful when we talk about exponential functions. So will this one. Let's look at some more power functions though. So kind of the classic one here. It's just x to the negative 1. And if we want to get a feel for this guy, we can make a table. I don't know if you guys have seen the graph of this function before, but so if we use the input -3, right, x to the negative 1, then I'll have -3 to the negative 1 for my output. If I use the input -2, then my output will be -2 to the negative 1. If I use the input -1, my output will be -1 to the negative 1. If I use the input 0, all right, you get the idea. Like this. But what are these numbers? You could feed these to your calculator. You could, and it'll give you a decimal and that'll give you some idea. But the smart move here, if you really want to start understanding what's going on with these things, the smart move here is to rewrite these using positive exponents. And let's start at the bottom and work our way up. What is 3 to the negative 1? Can we rewrite that using positive exponents? As a common exercise back in 1033. Yeah, this is 1/3, right? This is 1 over 3 to the 1. And 2 to the negative 1, that's 1/2. 1 to the negative 1, that's 1, because it's 1 over 1. What about 0 to the negative 1? One over 0, what is that? Like, I can't divide by 0. Yeah, good, Kendra. This is an undefined quantity, right? Just because you can write it down doesn't mean it's something that makes sense. 0 to the negative 1 looks reasonable when you write it like this, but when you rewrite it as a fraction, you're like, oh shit, this is actually dividing by 0. This would be 1 over 0. That's certainly undefined. And then negative 1 to the negative 1? Well, this would be 1 over negative 1, which is negative 1. Negative 2 to the negative 1 is negative 1/2. And negative 3 to the negative 1 is negative 1/3. So I can sketch the graph of this function. I'll mark this as 1. I'll mark this as negative 1. And we'll go 1, 2, 3, 1, 2, 3. Malakity, be good. Ever since I moved, the cat's decided that she wants to destroy the couch. All right. So if I start over here, when x is negative 3, the output is negative 1/3. Well, negative 1/3, this would be like negative 1/2. Negative 1/3 is going to be like right here. So here's the point, negative 3 comma negative 1/3. Then I've got negative 2 comma negative 1/2. And then negative 1 comma negative 1. 0 were undefined. And then 1 comma 1. 2 comma 1/2. And 3 comma 1/3. That looks like this. What I want to know is what's happening here. Like, I don't have a y-intercept because this function is undefined at 0. But what's happening as we get closer and closer to 0? It might be helpful to look at the inputs 1/2 and negative 1/2. So here's a fun one. What is 1/2 to the negative first power? Well, if I follow the same rule I was using for all of these, this should be 1 divided by, parentheses, 1/2. And if you divide 1 by the fraction 1/2, you get 2. All right, because this is like 1 over 1 divided by 1 over 2. So you flip the bottom over and multiply by the top. Negative 1/2 to the negative first. This would be 1 divided by negative 1/2, which is going to be negative 2. So here's negative 1/2. And that output is going to be all the way down here at negative 2. Here's positive 1/2. And this output is going to be all the way up here at positive 2. So the shape of this graph is interesting. It's like getting steeper and steeper as you get closer and closer to 0. And then as your x values walk further and further away from 0, it's getting shallower and shallower and starting to sort of settle down on the x-axis. Does anybody know the name for that sort of behavior? Anybody ever seen a graph like this before, where it sort of settles down on something as you walk way, way out to the right? Or it sort of blows up at some point in the middle here? They're called asymptotes. So what we're finding here, what we're seeing by graphing these very carefully, is that the function 1 over x has asymptotes. If you go way up here, you see this, here's the points we graphed. Here's like 2, 2, 1/2. And then here's 1/2, 2, 1/4, 4, and it blows up like this. Also, as you wander really far out to the right, it settles down on the x-axis like this. This shape, where you've got like a curve here and a curve here, and they're kind of facing off each other like that, this is called a hyperbola. If you've ever heard the word hyperbolic, that's where this term comes from. So we call these things asymptotes. And power functions with negative powers have asymptotes. So this is a sort of new feature, right? This is something we haven't seen in the past. Is new to these power functions with negative powers. So just like we did with the power function with positive powers, there's some graph shapes I need you guys to learn. Are there any questions about this graph? X to the -1, of course. If we weren't thinking of it as a power function, normally you write this as 1 over x. But right now we're thinking of it as a power function. So we want to make sure to write it as a power function. Some graph shapes. Okay, and we'll do the end behavior too. So there's the graph we just looked at. And the good news is the quadrant 1 graph shapes here, there's really only one of them. All of these functions in quadrant 1, all of these power functions where the power is negative, have like this quadrant 1 graph shape. Now, if the power, so these are functions of the form f of x equals, what did we use? Like c times x to the p. This is where the power is negative and the coefficient is positive. And this is the power is negative and the coefficient is negative. And it is possible, depending on what you're looking at, if the power happens to be a negative integer, a negative odd integer, you'll have another little piece down here. And if the power happens to be a negative even integer, then you'll have another piece over here. For the first quadrant picture, there's just the two possibilities, this, or I guess this is the first quadrant over here. And then the same thing is true here, right? If you have if P is a negative even integer, you'll have a piece down here matching this one. And if P is an odd negative integer, then you'll have a piece here like this. So the examples you should be thinking of here are like x to the -1, x to the -2, x to the -3. Those are your sort of basic graphs. X to the -1 is the one we've looked at, right? This is 1 over x. X to the -2 has the y-axis symmetry. This is an even function, right? Because the only powers that show up here are even integers. X to the -3, this is an odd function. And again, you've got this sort of graph shape that we're talking about here, right? You've got a piece in quadrant 1 that looks like this. And because P is an odd negative integer, you've got a piece in quadrant 4 that looks like this. P to the -4, piece in quadrant 1 that looks like this. And because P is an even negative integer, you've got a piece in quadrant 2 that looks like this. If I look at -2 times x to the -3, you've got a piece down here in quadrant 4 that looks like this. And you've got a piece up here that looks like this, because P is an odd negative integer. And if I change this to a -2, you see the two pieces we're talking about here, this and this. All of these have the same end behavior. So what is that end behavior? As x goes towards -infinity, y goes towards where? And as x goes towards +infinity, y goes towards where? Well, help me out. So if I'm on the graph of one of these functions and x is going way out here towards -infinity, what are the y values on the graph getting closer and closer to? Look at the y values there, you see them? -0.006, 0.004. Those y values are all getting, closer and closer to 0. And the same is true as we wander off to the right. Yeah, this graph is kind of trying to sit down on the x-axis in that same way. As I wander off to the right, these are all going towards 0. And it doesn't actually matter what the power is, as long as the power is negative. It doesn't matter what the coefficient is, as long as the coefficient, it really doesn't matter what the coefficient is. It's like x to the -1 here. As you wander further and further off to the right, these y values really are getting closer and closer to 0. 0.92, 0.08. So in both directions, these y values are going towards 0 as x goes very far off to the left or very far off to the right. I know that these sort of memorizing graphs might not seem exciting to you, and I understand that. Here's my advice to get around this, right? This is boring, I get that. You don't want to sit here and just memorize graph pictures. Every time you're solving a homework problem, I want you to graph the function. Why is this still loading? That will solve this issue for you, and it'll save you from having to sit there and like do flashcards or something stupid like that. If every time you encounter one of these functions, you graph it, you will learn these graphs automatically. And it might even give you some extra insight into the problem. So having done that, let's take a look. Oh, that's right. We need to introduce the proportionality language here too. One last set of then we can solve some problems. So far we've learned about direct proportionality and joint proportionality. Inverse proportionality is defined as follows. We say y is inversely proportional to x or varies inversely as x, provided y is equal to some constant times 1 over x. All right, that's the idea. Or you can write it as k over x if you want. For some constant k. So if I say that one thing varies inversely with another thing, I mean that they're related by an equation like this, that one is equal to a constant times the reciprocal of the other. So for example, if I say y varies inversely as x cubed, this means that y is equal to some constant times 1 over x cubed. Make sense? So varies inversely just means equal to a constant times the reciprocal of. All right, having done this, we can look at some things. So the first few problems here are a little bit silly. I don't want to waste your time on something that is quite that simple. But number 4 is interesting here, but it's not really the type of problem that we're going to put with. Maybe I will grab one of the simple ones to start. Yeah, fuck it, let's do it. All right. So number 2 here says y varies inversely as x, and y is 11 when x is equal to 4. So homework 11, problem 2. They want us to find, wow, that should really be a period. That's bad grammar. Yeah, okay. Those of you who have finished 1102 recognize everything up to the 4 here as being a complete sentence. And this is a new sentence with a new verb and a new subject. That's really bad grammar. Find y when x is equal to 6. Okay. So what we need to do is treat this like the other proportionality problems. We need to take some bit of this information, namely this, and write down an equation. Then we're going to take some other bit of what they gave us, this, and solve for k. That will allow us to update our equation. And finally, once we have our updated equation, we can answer whatever question we want. The fact that y varies inversely as x tells me that y is equal to some constant times 1 over x. That's what that means. Now they've told me that y is 11 when x is 4. So 11 must be equal to k times 1 over 4. And this means multiply both sides by 4, that 44 is equal to k. So we can update our equation. Y must be equal to 44 times 1 over x. And now if I want to find y when x is 6, I just plug in x equals 6. So when x is equal to 6, we have y equals 44 times 1 over 6, which is just 44/6. Now 44 is not divisible by 6. 48 is divisible by 6. 42 is divisible by 6. 44 is not. However, they do have a common factor. All right, this is the same as 22 over 3. If you divide top and bottom by 2. So this is kind of as simple as one of these problems can get. Are there any questions about any of these one steps? When I say simple, I don't mean they're like trivial. You know, it's just good practice with the notation and the language. Yeah, I'd be happy to look at number 4. Before we move away from this, are we all very comfortable with how this part corresponds to this? How this is what we need to solve for k? All right, so we plug those bits in. And then kind of this is really the victory step, where I can go back to this equation, but plug in what k is. Once I have this, I know everything. I could find y when x is 6. I could find x when y is 12. I could find out what happens to y when x triples. I could do all of them. Last call for questions. Okay. So Mark wanted to see number 4. Yeah, we can do this, but choose x equals 3 and 4. I don't quite understand the question there, Mark. What do you mean by choose x equals 3 and 4? I'd be happy to solve that problem. Let me get this copied down and we'll see where we can go from there. So they tell me, this is homework 11, number 4. They tell me y is equal to k over x to the n. I'll write it as k times 1 over x to the n. All right, for some numbers k and n. Based on the table, find k and n. And the table here is some x's and y's. The x's are 2, 4, 6, and 8. And the y corresponding to 2 is 22.5. The y corresponding to 4 is 11.25. The y corresponding to 6 is 7.5. And the y corresponding to 8 is 5.25. 1.625. This problem is a little bit tricky. But it is similar to the things we were just doing, where we're going to take the information they gave us, plug into the equation, and try to figure out the constants k and n. So what I would do here is I would just start plugging things in, see what I get. So I know that y is 22.5 when x is 2. So 22.5 must be equal to k times 1 over 2 to the n. I also know that 11.25 must be equal to k times 1 over 4 to the n. And we can keep going like this. I know that 7.5 must be equal to k times 1 over 6 to the n. And I know that 5.625 must be equal to k times 1 over 8 to the n. All right, so I'm just taking each little bit of this table, the ordered pair 2, 22.5, and plugging it in for x and y in this equation. That gives me this. One of the things I can do here is solve for one of the variables in terms of one of the others. So I could, what's the right way to say this that won't be confusing? I could try to solve this for k and then plug that in down here and see what I get. Or I could try to solve this, but I don't have the power to do that. So let me do it like this. Yeah, let's say from this guy, because you guys don't know about logs yet. From this guy, if I multiply both sides by 2 to the n, I'll get 2 to the n times 22.5 equals k. And now I could plug that in here, or here, or here. All right? So let's take that and plug it in here. This is called substitution. Really what we're doing here is we're solving a system of equations. You could think of just these two as a system of equations. I'll number these. Let's do it that way so I can refer to them. Now plugging this k value into equation 2, I get 11.25 is equal to k, which is this, 2 to the n times 22.5 times 1 over 4 to the n. Now we're going to see what we can do with this. Everything here is being multiplied. So I can do away with the parentheses. This is the same as 11.25 equals 2 to the n times 22.5 times 1 over 4 to the n. I can divide both sides by 22.5. Or let me do it like this. I'll shuffle this over here. And then I'll divide both sides by 22.5. Do I have y it up? No. The fun stuff is going to come from combining these, which is where you're going to need those exponent rules that I showed you at the start of class. But first, let's go ahead and divide both sides by 22.5. On the right-hand side, the 22.5s are just going to cancel and go away. But what about on the left-hand side? What is 11.25 divided by 22.5? 0.5. It's exactly 0.5. It's exactly 1/2. And then over here we have 2 to the n times 1/4 to the n. Who can help me combine 2 to the n times 1/4 to the n? How does this work? Remember your exponent rules. So 0.5 is the same as 1/2. And this is the same as 2 to the n over 4 to the n. So what we have here is 1/2 is equal to 2 over 4 to the n. Right? I'm using here this rule. On the right-hand side, you guys see it? A to the n over b to the n is equal to a over b to the n. 2 to the n over 4 to the n is equal to 2 over 4 to the n. What is 2 over 4? Yeah, good, thank you, it's 1/2. So what we get here is 1/2 is equal to 1/2 to the n. So here's a fun question kind of looking forwards. What power n works? What power n can make this a true statement? One, right? How is it possible to have 1/2 equal to some power of 1/2? Well, the only way that's possible is if the power is 1. Right? Because over here, this is 1/2. This side is really 1/2 to the 1. Everything is itself to the 1. So this tells me, boom, n must be equal to 1. And now that I have n, finding k will be easy, right? Now that I have n, this is just like all the other proportionality problems. I want you to take a second and make sure that your notes here are clear. These sort of problems tend to be a little bit challenging. So I really want to make sure that you guys are comfy with what's going on. Does everybody understand what we did? This first step, I took this equation and I solved it for k. I was able to do that just by multiplying both sides by 2 to the n to get rid of this 1 over 2 to the n. That gets me here. Now I take this and I substitute it in here, right? Specifically right here. I know k is 2 to the n times 22.5. So this k right here, I can replace by 2 to the n times 22.5. And the rest of this equation is the rest of this equation. From there, I just cleaned things up. Just did some multiplication here. I was able to get rid of these parentheses because everything's being multiplied. I changed the order of multiplication, right? Because 1 times 5 times 7 is the same as 1 times 7 times 5. I just shuffled this 2 to the n over on the other side of 22.5. That's okay, because they're all being multiplied. You can do multiplication whatever order you want. And then we tried to simplify. Brooke asks a really good question. Could I have plugged that k into any of these equations? Yes, ma'am. If I went and plugged that k back into the same equation I solved for, if I went and plugged this k back into equation 1, then I wouldn't get anything new. I would just simplify to like 1 equals 1 or 0 equals 0. But I could have plugged that k into any of these and gotten the same thing. The reason I chose this one is because I thought the 1 over 2 to the n and the 1 over 4 to the n would simplify nicely together, right? Like 2 and 4, they're both powers of 2. I wouldn't want to do it with this one because this guy has a factor of 3 that might make it a little bit trickier. So I chose the second one because it was the one that looked most similar to the first one. But yeah, you could have done it with any of them. It would have worked out the same. Now that I know n, I have to find k. So let's update equation 1 with the value of n that we just found. All right, so I'm happy with n. I know what n is. N must be 1. So I can take this equation and plug in n equals 1. I can do it with any of these. All right? There's nothing stopping me from doing it with any particular one. But I might as well just go back and use equation 1. That'll give me 22.5 equals k times 1 over 2 to the 1, which is the same as saying 22.5 is equal to k times just good old 1/2. And then to get rid of the 1/2, I just multiply both sides by 2. So we can be careful with our arithmetic, it never hurts. 45. And that does it. Now we know both k and n. Is this making sense? All right, take a second, make sure your notes are nice and clear. If you have any questions, now is a really good time to ask. Okay. So the other sort of things that I want to look at with you guys today, there are a handful of problems relating to graph shapes, like we talked about. I think it couldn't hurt to look at 1 or 2 of these. I don't want to spoil them all for you. So what are they having us do here? They want us to find, evaluate these, sketch the graph, domain range. Increasing, decreasing. All right. So I'm not going to do exactly this problem, but I'll do one very similar. Did they give us a non-trivial coefficient? Yeah, okay. Negative next to -2. We want to evaluate at a few points. Decreasing. decreasing, and then this is also symmetry, increasing, decreasing, and behavior. And then, yeah, parity. All right, so I'm condensing this as much as I can, but let's do it. We have here a power function with a negative power. We want to evaluate the function at some values, some inputs. We want to sketch a graph and find the domain and range. We want to answer, where is this thing increasing and decreasing? And can you tell me the end behavior? And then this has to do with symmetry, but they just phrase it like that, right? This is all they say here is, does this satisfy this? Is F even or odd? Or neither? Certainly it's possible that neither of those are true. So let's get to our answers. Part A. F of -2 would be what I get when I plug in -2 for x. Now, a word of advice, anytime you're plugging stuff into a function, always do so in parentheses, right? When you're replacing your variable by something, please, please, please put the thing in parentheses. So this is negative parentheses, -2 to the -2, like that. These parentheses, I promise, will save your ass. 100% promise you that. There are lots of questions you will get wrong if you don't do this. You'll get them right every time if you do this, and it'll help you all the way through the math sequence. So anytime you're plugging into a function, do so in parens. Now I could feed this to my calculator, but that's the lazy way to do it. This is the same as -1 over -2 to the +2, right? This power here says put him downstairs and raise him to the positive version of me. And now this is -1 over, what is -2 squared? If I multiply -2 by itself, what do I get? Four, good. -2 times -2 is +4. So this is -1/4, done, right? Faster than a calculator, if you think about it. F of -1 is -1 to the -2, which is -1 over -1 squared. Well, shit, what's -1 squared? It's -1 times -1, that's +1. So this is -1 over 1, or just -1. F of 0, that's -0 to the -2, which would be -1 over 0 squared, which would be -1 over 0, which is definitely undefined. We cannot divide anything by 0. F of 1 is -1 to the -1, like this. Again, the parentheses are going to be important here. That's the negative of 1 over, oh, sorry, this is a square, isn't it? I'm sorry, I'm so sorry. Yeah, the power is -2. So this is -1 to the -2, which is -1 over 1 squared, which is -1 over 1, which is -1. And F of 2 is -2 raised to the -2nd power, which is -1 over 2 squared, which is -1/4. So what do you notice here? F of -2 is -1/4. F of +2 is -1/4. F of -1 is -1. F of +1 is -1. So F of -2 is the same as F of 2. F of -1 is the same as F of 1. Which one of these expressions appears to be satisfied comparing these things? Is it this? Is F of -x equal to F of x? Or is it this? Is F of -x equal to the negative of F of x? So I said this is the same as this. They're both -1/4. This is the same as this. I'll let you think about it for a second. If I wanted to start graphing the function, I could do it based on these. But I think it's also wise to get comfortable looking at this thing in your graphing calculator. So if I want to input this function into my graphing calculator, I do it like this. I hit y equals, and then I want to input -x raised to the power of, and really we should put this in parentheses, -2. All right. And then I can hit graph. Now here's the picture I get. It doesn't really tell me a lot. It kind of looks like it stops here, kind of looks like it stops here, but it doesn't. It just looks that way. And if you want to, you can fiddle with your window settings. All right, maybe this is too broad a window. So I should swap this maybe for -5. And this maybe for +5. I should swap this maybe for like -5. This maybe for +5. Let's just zoom in a little bit. Let's see a little bit better what's going on there. So it's not that the thing stops here. It's just that it gets really close to the y-axis. If I wanted to change my y scale a little bit, change it to like 0.1. See what we get. Maybe we get something a little better. A little better. We could try zooming in a little further if we wanted to. Just to give you some perspective, here's that same graph in Desmos. All right. And you see that it doesn't ever stop. It keeps going on and on and on forever in each of these directions. So the graphing calculator is a useful tool, but it can be a little bit misleading. You guys see the differences? Can you see what I'm talking about? The graphing calculator appears to say that this domain chops off like here and here, but it does not. It does not. It goes on and on forever in both directions. And then right here at 0, we're diving all the way down to -infinity. So it doesn't like stop here either. It just keeps going down further and further and further. Okay, well, we've got lots of good stuff now to sketch our graph. So let's sketch our graph. Here's the graph. Doesn't have to be a perfect work of art, but what I will ask you guys to do is every time you're sketching a graph, make sure you label at least 3 points. So we know it gets really close to the x-axis here and then dives down. Something like this. Really close to the x-axis here and dives down. Like this. Okay. So this is a reasonable picture of my graph. And I can add a few points onto this, right? Like, how about -1, right? F of -1 is -1. So the point -1, -1 is on here. And we'll label it -1, -1. +1, -1 is on there. Let's do that. There's 1, -1. And then 2, -1/4 is on there also, right? F of 2 is -1/4. So here's a lovely graph. All right. If this were an exam and I asked you guys to draw the graph, 100%, full points, beautiful graph. What's the domain of this function? In interval notation, por favor. It's not all real numbers. It's a little different. I should ask, maybe what number is not in the domain? Yeah, perfect, Mark, thank you. right? It's everything but 0. This function is undefined when we try to plug in 0. So 0 is not in the domain. This piece tells me that x equals 0 is not in the domain. So my domain is -infinity up to, but not including 0, unioned with 0 to infinity. And you can see that also using the squishing game, right? The smooshing game. If we were to smoosh this whole graph up onto the x-axis, the only piece that doesn't get hit is right here at 0. This piece would smoosh down to here. This piece would smoosh down to here. What about my range? Is +1 in my range? Is +2 in my range? Perfect, Kendra, thank you. Yeah, if I smoosh this graph down onto the y-axis, like horizontally like this, there is no graph up here. There's nothing that's going to hit any of the positive numbers, but all the negative numbers get hit. This is -infinity up to, but not including 0. Very good. Okay, so these are our domain and range. We want to answer, where is this function increasing and where is this function decreasing? And remember the way we answer this. It's always open intervals of x values. So if I'm a little dude walking along the graph from left to right, I'm going downhill, 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 downhill. And then over here, I'm going uphill, 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 uphill. So where is f of x increasing? For what x values do I go uphill? Very good, from 0 to infinity. Kendra's got it. We are increasing everywhere along here. So the x values for which we are increasing are 0 to infinity, right? Everywhere along this part of the graph, we are increasing, which means we're increasing from 0 to infinity, not including 0. Where are we decreasing? For what x values are we wandering downhill as we go left to right along the graph? Excellent, Brooke. Yeah, from -infinity to 0, right? As I'm walking along this whole part of the graph, I'm going down, 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 down. So what are those x values? Well, all the way out at -infinity, all the way up until 0, we're going downhill. I'll avoid the Nelly joke. Lastly, what kind of symmetries do we have here? Is f of -x, so this is the question I asked you guys earlier based on the table. Does f of -x appear to be equal to f of x? Is f of -x equal to the negative of f of x? Is f even? Is f odd? And remember, these are connected to each other. These two are rephrasings of these two, and each one corresponds to a certain kind of symmetry. What kind of symmetry does this graph have? Or it could have no symmetry. But I claim that this one does have some kind of symmetry, and I'd like you to tell me what kind of symmetry. Yeah, it has y-axis symmetry, right? It's symmetric about the y-axis. So what does that mean? Does that mean it's an even function or an odd function or neither? Very good, yeah. So this is an even function because the graph has y-axis symmetry. Okay, so we are an even function. Are we also an odd function? Is that possible? No, right? Now, which one of these two is true? Which one of these corresponds to an even function? Good, Logan. Yeah, the first one. And if you want some explicit examples here, this is, you could say, because this is the definition of an even function. Or you could observe that f of -1 is the same as f of 1. They're both -1, right? F of -1 is the same as f of 1. The y values here are the same. F of -2 is the same as f of +2, and so on. So yeah, this is the answer to the symmetry question. Okay, do you guys have questions for me about this problem? I feel like if you fully understand this problem, you're in really good shape with this stuff. Yes, you do. Yeah, you got to know these basic graph shapes. Yep. All of them, positive and negative power functions. Altogether, there's like 8 shapes here that we have to learn. You can use the TI-83 or TI-84 on the tests. Yep. But you do need to know the graph shapes also, because there can be clever questions that you cannot calculator your way through. For example, oh shit, did this really boot me out? Here we go. So if you look at some of these other questions like here, sorry, my wife's texting me. Here on this question, they give us the graph, but they don't give us the formula. And they ask all these same sort of things, like even or odd, is the coefficient positive or negative? Where's the function positive? Where's the function decreasing? All of these are the sort of things that, you know, especially these first few, if you had the formula, you could put it in a graph calculator to figure out or something like that. But we don't. So we need to be able to go back and forth using just our brain. We need to know those basic graph shapes. That is a true thing. Other questions on this? Okay, I would like to look at one more thing. Let's do this guy. Say, suppose y is equal to -3x to the -2. If x doubles, what happens to y? And our choices here are y gets multiplied by something, or y gets divided by something, and then by what? Is it safe to say that even graphs reflect algebra? Kendra asks a neat question in the chat here. Is it safe to say that even graphs reflect left to right? Yes, yes it is. And is it safe to say that odd graphs reflect diagonally? You have to be a little bit careful with that last one. So odd functions reflect over the origin. So you can think of it as reflecting both. Let me show you an example that's something way outside our wheelhouse. Odd functions reflect not necessarily diagonally, but if you were to flip them vertically and flip them horizontally, they sit on themselves. Or you can think of it as reflecting through the origin. Or like this, right? So if you were to flip him over horizontally, it would look like this. And then if you flipped that over vertically, it'd look like this. So if you do both the horizontal flip and the vertical flip and you sit back on yourself, that is an odd function. All right. So let's come back to this guy. I want to know if x doubles, what happens to y? Well, x doubling means replacing x by 2x, right? If I double something, I'm multiplying that thing by 2. So what would y be? Y would be -3 times the double of x, 2x, raised to the -2. So that's the same as saying y equals -3. Now we need to use those rules for exponents that we had at the start, right? A times b to the n is the same as a to the n times b to the n. And of course, it's all being multiplied. Now there's nothing I can do with the 3, but 2 to the -2, I can work with that. 2 to the -2, that's 1 over 2 squared. X to the -2, I'll leave that alone because I want to compare this to the original thing. So this is 1/4. And then if you want, you can kind of shuffle this around. This is 1/4 times -3x to the -2. And this right here is my old function, my old y. So what happens? Well, you could say that y gets multiplied by 1/4, or you could say that x gets divided by 4. So when x doubles, I think most people would say it the second way. Y gets divided by 4. Or you could say, this is the same as saying y gets multiplied by 1/4. But I think they're going to want the first thing here. And specifically, the big idea is that with these power functions, when the power is negative, if you increase the x value, the y value goes down, right? I doubled the x value, and the y value gets divided by 4. So these inversely proportional things usually mean as the input gets larger, the output gets smaller, which is kind of backwards from the direct proportional things. Now, of course, that kind of depends on the coefficient, depends on a few other things, but that's the basic idea. And this is where we're going to end for today. That's everything you need to knock out homeworks 10 and 11. Please take your time to think carefully about these problems as you solve them. Make sure you try to understand them all the way. Don't be shy about asking for help, coming by office hours, talking to me through Canvas, anything. Any communication is good. And if you're struggling with something, really don't hesitate to ask. The tutors at the Learning Commons are pretty good at this stuff. You can ask them for help. But of course, I'm your professor, so don't hesitate to ask me for help either. Is there anything I can do for you guys before we sign out here? Can get into the test reflection. Okay, I do need you guys to complete the test reflections. What's going on here? Assignments. Is this test 1 reflection? It shouldn't have any restrictions. I don't have any due dates or anything like that set in here. Let me just see here. Maybe I need to make it available. It says unpublished. Oh, weird. So this is something that the college is running sort of remotely. Let me see if there's, I'm gonna turn off the screen share for a second. Is there a, and it says published here. Yeah, you know, I don't know, I'm showing you guys. It says here that the thing is published. Show rubric, delete. Let me just add an availability date here. I'll make it available from February 1st at midnight. And we'll see if that fixes it. All right. Do try to get in there. It'd be nice to earn those extra credit points. I'm sure everybody wants those. Doesn't hurt, even if you have a nice score already. Let's see. So when I added the available date, it gave me this published thing up here. So hopefully that'll do the job. So yeah, thank you for letting me know. Please do try to get in and complete the test reflection. And if there's anything I can help you guys with, don't hesitate to reach out. Take care.